today. In my mind, some of these chapters, the concepts are pretty straightforward. There's just a few key ones. This one seems more full to me. So that's why it's stretching over more than our standard number of lectures. So we started with two types of charges, positive and negative. They come from protons and electrons inside atoms. Everything's made up of charges. Kurt, do you think you're charged positively or negatively? Both. Yeah, mostly they're in balance, so I'd say you're neutral. How about this 2x4? Does that mean it doesn't have charges? Correct. It's definitely got charges. It's made up of atoms. I'm made up of atoms. Okay, I got it. All right. Never trust an atom. They make up everything. Okay. I should have wore that T-shirt today. Now I think about it, I have that T-shirt. Oh well. So if you got two positive charges, do you remember what's the forces between them? Two positive charges. You got two. That's right. They repel. This one feels a force, and this one feels a force. How do you think those forces compare? Equal and opposite. Newton's third law. You got it. How about two negative charges? That's right. By the way, the charge on a proton is the same charge as an electron. They're just opposite charges. And a positive and a negative. Yeah, their masses are different, protons and electrons, but the charge is the same. And that's right, these attract. So this one exerts a force this way, and this one is pulled that way. Well, Coulomb's law is the law that guides our thinking to these forces. You guys are familiar with forces now. The force is proportional to the charge. It's usually represented by a letter Q. That's the charge, no matter whether it's positive or negative. And it depends on both charges. What's Newton's third law? Equal and opposite. Every action, there's an equal and opposite reaction. Good, good. Well, forces are equal and opposite. The action-reaction. Good, good. It's good to review. Just seeing what else you got. My favorite way of defining Newton's third law, everything you said is right, is all forces come in pairs. It's an interaction. I can't interact with you without you interacting with me, whether you like it or not. Because if I go and push on you, you push back on me. So if these two charges are interacting, as we just discussed, then it depends on both charges, Q1 and Q2. It's proportional to both of them. Remember, if you have one big mass and one little mass, the mosquito or the bug hitting the windshield, who feels more force? They're equal. But wait, they have different masses. Same idea here. You could have a big charge here and a little charge here. How does the force on little q compare to the force that big Q feels? It's the same. Let's say they're both positive. Then they repel. But it's the same force. This force is dependent on both of them. This one, the force on little q is dependent on its charge and this charge, and vice versa. So it's the same magnitude of force. It's just it can be in opposite directions. Well, it is in opposite directions. They have different masses, so I'll address that part first, a proton and an electron. So if you had a proton and an electron, you know, the forces are the same. We just did that. So tell me about their accelerations. Right. The electron will be accelerated more. This will have a bigger acceleration than that one. Why? Because little mass, big mass for the same force. They happen to have the same charge, but that's not why they feel the same force. That's this example. Here's a lot of charge, little charge. Think of it this way. You could have 1,000 protons and 1 electron. There'd be 1,000 as much charge over here as there is here. But the force that each feels is the same. It'll be 1,000 times more force than if you just had 1 proton and an electron. But each one will feel 1,000 times more force. That's part of Coulomb's law. It depends on both charges. Does that make sense? It also depends on the distance between them. I bet you could have guessed that. If you have a proton and an electron this close together, do you think they're going to get pulled together with a stronger force than if they're this far apart? Yeah, the closer you are together, the stronger the force. So it's proportional. And it actually works out to be what we call an inverse square law. It's proportional to the distance squared, similar to kinetic energy, 1/2 mv squared. Here's a visual representation of the inverse square law. If you're here at this point, the vertex, and you are right at this point, you're this far away. You're this far away. Then you cover like 1 square. That's going to represent the force you'd feel. If you are 2 times as far away, it's not twice. The force doesn't change by a factor of 2. It changes by a factor of 2 squared. 4. See how it covers? See, we haven't changed the lines, how it spreads out, but now it covers 4 squares. Likewise, if you're 3 times as far away, you feel 3 squared less of the force. Yeah, so you feel 1/9 of the force this far away as you do this far away. That's the inverse square law. Put all these together, and that is Coulomb's law. It is the force is proportional to Q1 times Q2 over d squared. It's directly proportional to the charges. As those are bigger, the force is bigger. But as the distance increases, the force decreases. And it's exactly equal to, this is a constant of proportionality. It's Boltzmann's constant, and it's a, did I write that down anywhere? It's about 9 billion. So it's a really big number. What that tells us is the electrostatic force between charges is huge compared to the forces we deal with. Compared to just gravity. If you have 2 masses, you know, they attract through gravitation. The gravitational force between a proton and an electron is completely and utterly negligible compared to the Coulomb electrostatic force between them. Electrostatic force is huge. So it's almost like you turn gravity off. You can ignore it because it essentially has no effect compared to this electrostatic force. And that's all because this constant represents that. It's like about 9 billion. But there you go. That's Coulomb's law, and that'll guide our thinking to forces between all these charges and how we can get them to move around and why they attract and repel and whatnot. So here's an example. If you pull tape off of a roll, I just separated 2 materials, this off the roll. So this became charged. Watch, it attracts my finger. So you can tell there's charge on it. What's it doing to the charges in my finger? What charges are in my finger? Positive and negative. So what's it doing to those charges? Polarizing it. It's inducing a charge in my finger and polarizing these charges. Let's say the tape is negative. We don't know. What's it do to the negatives? Repels them, pushes them a little farther away, that way, and attracts the positives. The positives are now closer to the tape than the negatives. If they're closer, the attraction force is stronger now than the repulsion force of the negatives that are further away. Did you follow that? There's still positive and negatives. It's attracting the positives and repelling the negatives, but if the positives are more close to the tape, that force wins and it attracts. All right, let's fold that over. Set it there. Do a second one. Should be charged the same way. Yep, okay, good. Ah! Now you know how a cat feels when you put tape on its claws. It's really cruel. No, I have not done it. But I've watched people do it. These are the same charge. What do you expect to happen when I bring them together? Yep. And it's not some inherent sticky force. It doesn't matter which side. But then it's fun. You can set them down on the table. Come on. This is the real reason I fold the lip over. It's so I can get them back off the table when I'm done here. Put them together. Trying to neutralize it. Get any excess charge off. So now the charges are balanced. Let's see. Yeah, it's not attracted to my finger. Pull them apart. Separate materials. One of these just grabbed more electrons than the other. They should be oppositely charged. How do we tell? Oop, they attract. They attract. They're oppositely charged. You can see that one attracts to my finger, but so does this one. It doesn't matter whether it's positive or negative. It still attracts to something neutral. Before we assumed this was negative, so it attracts the positives in my finger. What if it's positive? Well, then it attracts the negatives in my finger. So either way, it can polarize the charges of my finger. That's kind of fun. That's exact. Oh, yes. Yeah, let me draw a picture then. So if this is the tape, and let's say it's negative. Now, to be accurate, this has positive charges, and it has negative charges, right? So when we say something's negative, we just say there's more negatives on it than positives. But it's easier to just draw that sometimes. But as we start out, you should know what we're talking about. So if there's more negatives than positives, then this has a net negative charge. You bring your finger in that is made up of a bunch of positives and negatives also. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. There, I got them balanced. My finger's neutral. Those charges, what are they going to do when it gets near the tape? That's right. This is an exaggeration, but the positives are going to be more on this side, and the negatives on that side. In reality, they're not free to move quite so much. It's like you have an atom here. And the atom kind of becomes elongated, where the plus is on this side and the minus on that side. So it's kind of like there's this net effect. Yeah, if you're familiar with dipole, it's exactly what it does. But the way to think about it is, yes, the positives are getting attracted and the negatives repelled. So we say this is polarized. We've induced a charge. On the finger. That's what happens when you rub a balloon on your hair. I used to do this with a big balloon in my hair, but oops, not that. This works so much nicer. There's more surface area. Here's the balloon, here's the hair. All I have to do is do it once. Now this has charges. The door is neutral, but the balloon just polarized it. It did this to the charges in the door. And so it's attracting. And the Coulombic force is holding it on, overcoming its weight, so instead of falling down. That'll stay up our whole lecture. Probably stay till Monday if nobody messed with it. The tape idea is exactly how one of these works. Who knows what this is? Makes your hair stand up. It's called a Van de Graaff generator. And it has a roll of rubber, and it's just on a pulley at the bottom. It just goes around. The electricity, I plug this in, and the motor just makes the pulley spin. And every time the belt comes off the roller, charges separate. They follow the belt up and collect up here. So the charges are not coming from the power company. They're coming from the separation. You could do this with a hand crank. It gets tiring, so we automate it. And if you build up enough charge on this Van de Graaff generator dome up here, it'll all be the same charge. It's actually negative. It builds up. Enough that you can get these big sparks. Let's see if I can. Can you see that okay? That's literally miniature lightning. This is what happens in a lightning storm. Things rub in the cloud, air currents and molecules. Charges separate. The cloud becomes charged. Moves over the ground. Polarizes the ground. There's now two opposite charges that are trying to attract each other. If the difference in charge builds up enough, whammo, they jump through the air. They ionize the air molecules. Ionize, that means strip them of electrons. They become charged. And if they're charged, there's a conductive path to ground. Who would like to find out? Who would like to touch this? You'd be perfect. Would you help us? Yes. I'm going to move this. I'm not going to let it jump to that. I'm going to let it move and conduct onto her. So I'm going to ask her to stand on here and put her hand on this. And I wouldn't do this if it's not safe. You know that, right? Yeah. Okay. Have you done this before? Now, to make her safe, here's some precautions. Don't let go. Okay. Because if she lets go, then that keeps building up charge, and she doesn't. Now there'd be a difference in charge between the two, and it would try to jump like we just saw, and you wouldn't like that. Yeah. Don't touch me. I'm on ground. Okay. My charge, I'm neutral. So as you build up charge, if we touch each other, we'll both feel the force. We won't like that. Okay. And don't touch the table either. It'll jump there. So let's turn it on.
You turn it off and move my hand.
I would. Wait, yes. I'll remind you. If you do, it's not going to kill you. It just might be uncomfortable. Okay. So if you do all those things, you should be just fine. So charge is building up. We're separating charges. They're started to conduct on her. She can feel it already. If anything on her body is free to move, like her hair, it's the same charge, so it'll repel itself. Here, free it up. Kind of shake your hair. Here's what we see. They are actually following what we call electric field lines. Charges emit this imaginary electric field out into space. That's how other particles feel the force. They're in the electric field. her hair is trying to follow those field lines. They go out radially from her. Her head is charged. It's working great. We'll free you up here. Don't let go yet. Oh, they're getting a couple pictures. Now, I can go ahead and turn it off. She still has charge on her. She can let go now because we're not making a difference in charge. As soon as she touches the ground, some of that excess charge on her will, and some of you over here probably heard that little shh, and now her hair went down. Thank you very much. Do you guys, why do we have lightning rods? You ever seen those pointy things, the spiky things on the top of buildings? To attract the lightning? You even see them on the wings of airplanes, near gargoyles on top of buildings. Are they to attract lightning? Is that what you've heard?
That's what I heard.
It grounds the building. You can put it on your house, you know, so to speak. And it's true. They do attract lightning because they're conductors and they're high up. It's more likely to strike a conductor because it's the path of least resistance. It's easier than an insulator. Let's pause. What's the difference between an insulator and a conductor? Yeah. That's right. Here's plastic. It's an insulator. The electrons are too strongly bound to the atoms. They're not free to move around. So if I put charge on it right here, it can't go anywhere else. So there's charge on the electroscope. I charged it up earlier. It's still there. Do you see it? So I'm going to touch it. And you see the charge doesn't come off. Now, I did touch it right here, and there's some charge right there now, but that wasn't enough to notice any difference. How about a metal rod? Let's see. Sure enough. In metal, the electrons aren't as strongly bound to the atoms. They're free to jump from one neighboring atom to another, and that's what current is. It's the flow of charge, and they can move along. So that's a conductor. That's an insulator. What do you think wood will do? Let's charge this back up and try it. Here's a piece of wood. Conductor or insulator? Insulator? All right. Somewhere in between, but it seems to be more of a conductor right now than an insulator. I would never trust your life to wood. Wood's usually an insulator, but if it's really dry and it doesn't have oil or moisture in it, which can conduct, then you could fry yourself. If it's really, really dry, then maybe you're safer. But even if you put enough high voltage, is air conductive? Can be, if you get a big enough charge difference. But normally it helps insulate you. You don't see sparks just flying out of here, the outlets through the air, do you? But if we made a big enough voltage, they could. So yeah, anything can break down if you put a big enough voltage across it. So wood's kind of in the middle there. So that's what a conductor is. It can attract the lightning. And if lightning strikes your house, it's more likely to strike your lightning rod first. And so they usually have a cable going around your house to ground. Instead of going through all the wiring in your house and frying all your appliances and your computer. But that is not why we put a lightning rod on our house. This is why. Let's see how far it jumps. You can't all see it, but you can hear it. About that far. Let's put a lightning rod on the house. Now it doesn't strike. The main purpose for a lightning rod is to lessen the chances of your house being struck by lightning. What's going on, just so I can talk over, is the little sharp point creates a higher electric field. Basically more field lines. Picture her hair. They came off nice and radially. Well, they come off of this point. But that point's a sharper turn, so there's more lines coming off of there. What that means is the electric field's stronger right here. It ionizes the air, makes the air conductive by stripping them of electrons. there's a conductive path. So all the charges that are trying to build up on your house can leak off. It gives them a path to escape. If they escape, your house doesn't build up as much charge, there's not as big a difference, and you're less likely to get struck by lightning. With the lightning rod on the house, the cloud would have to become even more strongly charged or closer. There. So this just can't get to as high a voltage, as much charge. Here's another way to see that. Instead of bringing you back down with your hair, let's do this. Let's put the fur on here. That should do what her hair did. Woo! Zesty today. If you just have the lightning rod near it, it's like magic. You could hide this in your hand, and you could say, "Okay, hair, arise, down, back down. Okay, arise." That's what a lightning rod does. Again, it ionizes the air near the sharp points, so charge can bleed off. Ow! Now, if you get enough charges together, you can overcome the weight of a pie plate. Let's move enough charge onto those. If we can make the Coulomb force more than its weight, it'll accelerate up. Those are conductive, so the charge transferred, same charge, it repels. Let's do some packing peanuts. You ready? This one goes quickly. Woo! Oh, down my shirt. Okay. That's fun. And the balloon's still holding. That's good. So, after Christmas one day, a colleague sent an email to my listserv and said, "Hey, these are on sale." Anybody know what this is?
The Monster High Doll.
Very good. I didn't know if anybody was going to admit it. So, Monster High Freaky Fusion Chamber. And I saw the commercial, and it did this. Whoop. And I immediately said, there's got to be a Van de Graaff generator inside that. So I got one. There we go. I took it apart, and sure enough, it's just like that. There's a motor with a belt, and it just rolls. Same exact thing. Inside here, she touches it, and her hair stands up because the charge transfers. It's great. And you can see it go. It'll stay up for a while. Anybody seen one of these? It's a toy, about $20 to $30. It's called a Fun Fly Stick. Inside it is a little Van de Graaff generator. These don't get as strong as that. I can touch this. There's no shock at all. But it is a Van de Graaff generator, and it charges things up. So here's a little piece of foil, kind of like the tin foil plates over there. Touches, transfers charge, and repels. And now you can play Harry Potter. Wingardium Leviosa. Leviosa? Leviosa, whatever. Repels. What should it do if I bring my hand near it? It should attract to my hand. Yep. Neutralizes, falls back down till it touches, or attracts to me, touches this again, gets charged back up, and away we go. Doink. Static cling, touches, spreads back out, and away you go. A Fun Fly Stick. And I think that's cool. Gravity. Whoop. Coulomb's force. Countering gravity. It's that force between the charge. It's the charge on the stick and the charge on the foil. And the distance they are away from each other. Thank you. All right. To emphasize that this force can be strong, I'm going to move this 2x4 without touching it. Yeah, you're real excited. No. I'll use electric charge. But if we charge up one of these rods again, you can bring it near this. It'll induce the charges in the 2x4, make it polarized, and just like the balloon over there attracted to the door, the 2x4 is attracted to the rod. You can do it with the balloon. You can try it at home. You might not all have, rabbit fur and a rubber rod at home. But how about an oven bag and a plastic flamingo? Again, different materials. One of these likes electrons more than the other. Bring it near the 2x4, and sure enough, you can get it to move. One of my favorite quotes from my daughter from Big Hero 6, Fred, who's seen it? Science! Yeah! But anyway. Slow it back down and accelerate it back the other way. So these charges on here cause these attractive and repulsive forces. And it's through that electric field. Let's picture those. If you have a proton, the electric fields radiate outward. That's the electric field. They help us visualize what's going on around the charges. And how you figure out the direction is you take a positive test charge. If you put a test charge right over here, which way will it move? Towards the proton or away? Away, because they're positive. So that tells you that the electric field is in that direction. It goes that way. Notice I drew that arrow a little shorter. Why? That's right, it's further away. The electric field falls off with distance. The force is less with distance. A negative, an electron, it's still radial, but it comes inward, like this. That's the electric field. Again, if you took a positive test charge, it would be attracted. That's how you know it's towards the electron. Now, something else I want to emphasize. Electric fields can exist in space. There's an electric field right here, created by this charge. Is there a force here? No. How come? What's a force require? An interaction. So if you put a charge there, now there can be an interaction. You need to get a force through Coulomb's law. But the electric field can still exist there, whether there's a force or not. And they're related by this. The electric field is that force per charge. It's the force per charge. So look at this. If we have this little test charge right here, Q, it feels a force, we'll call it F. There's an electric field right here also. All right, you got that. Let's double the charge. Let's say it's 2 plus now, 2Q. What changes? So basically, we're going to take one charge and replace it, same spot, with twice the charge. What's different? Force. It has to be, right? We just changed the charge, and the force is dependent on the charge. And how much will it change? twice as much, so it'll feel twice as much force. Good. Does anything else change? The electric field? Let's look. We just doubled the force, but we also doubled the charge. Where I think electric field's nifty, neat, groovy, golly, whatever, the electric field doesn't change. For that same position in space, it's the same electric field, regardless of what charge you put there. So we can bring 1,000 protons and put them right here. That doesn't change the electric field. The electric field's created by who? By whom? This. We didn't change that, so it's the same electric field. Because the electric field is the force felt by an inserted charge per charge. It's the force per charge. So you double the charge, you also double the force, but the ratio stays the same, so it's still the same electric field. Does that make sense? Something I'd like you to note. You can apply that on the homework questions. Note this also, if we rearrange this formula. So you guys can see. Stay. Force is charge times the electric field. Does the form of that look familiar? Newton's second law was what? Mass times acceleration. There is a connection. The analogy holds. Anyway, a mass being accelerated feels a force. A charge in an electric field is accelerated, feels a force. It's that electric field that makes it accelerate. That's how the force is transmitted, so to speak. So if you forget this, maybe this can help, because you've already dealt with this a bit more. Instead of having a mass, we're looking at the charge of the object. And this is what accelerates it. This is what accelerates the charge. And energy holds true also. Let's do that one. Right here. All right. Gravitational potential energy. We're going to compare it to electric potential energy. Start with this one you're familiar with. Remind you, you have a mass. If you lift it up to here, up a certain height, and something we took for granted, but we talked about, this depended on gravity, the fact that we're in a gravitational field. It's directed down. We'll represent it with G. So to lift it up to there, does it take energy to raise it up? Yeah, you have to do work to get it up there. Yeah. Why? Because you're going against the field. It's trying to pull down. The force on it's acting down. And when you fight against that, it's like going upstream. You have to lift it up. You have to put energy in. So when it's up there, you now have potential energy. Remember what that was? The gravitational potential energy was mgh. This is the force times the distance. That's the work you put in. Well, it's totally analogous for a charge. Charge Q in an electric field, if we want to lift it up to here, move it a distance d. Can you see the similarity? Which way does this positive charge want to go in this electric field? Down. Yeah, the force is pushing it down. So you'd have to put energy in to move it against the field for that given distance. Over here, the force you have to apply Yeah, it's mass times gravity. Over here, the force is the charge times the electric field. Work, force times distance, mg times the distance, h. That becomes the gravitational potential energy. So do the same thing over here. Work is force times distance. The force is QE times the distance. That's the amount of energy you'd have to give the charge. And that becomes electrical potential energy. It's still in energy, still measured in joules like it was before. The only little difference here is these always go down. But what if we made this a negative charge? Which way does it want to go? Up. So it would release that same amount of energy instead of gain it, because it wants to go that way. For a negative charge, downhill is up in this diagram. So protons and electrons go opposite directions. We always stick with a positive test charge for our positive values. But it's the same idea. Questions? Yes?
How much is like one charge, one Q? Is it just one?
What's a typical value for a Q?
Is it just like one atom, or is it like one?
Q could be anything. If you just have one proton, the charge on a proton is, and I don't remember, 1 times 10 to some negative big number. It's a really small amount in Coulombs. I did forget to tell you that. The charge, the unit for charge is a Coulomb. But if you have 1,000 protons, then you'd multiply whatever the charge is of one proton times 1,000, and we'd say Q is now 1,000 of whatever that was. So Q represents the amount of charge for your system, so to speak, your particle, but it can be more than one actual particle. An ion could have a certain charge. We know it's because of adding up protons and electrons, but we can give it just one Q. So I'm really trying to emphasize, so it's familiar stuff. Because electric fields, we're now talking about invisible lines going out. That's why I like seeing her hair. Thank you again. But we're familiar with a gravitational field. Just picture an electric field. Masses moving in this field, charges moving in that field. They require forces, Coulomb's law. If you move them certain distances, you've done work, force times distance. And you've just changed its energy. So we're not to currents yet, but think of a battery or a power supply. What does it do to charges? It gives them energy. It's like it pumps them uphill, raises them up. They now have energy, electrical potential energy up here. Then they go around a circuit giving up that energy to power a light bulb or to run your computer or whatever. Then they get back to the battery, gain energy again, get bumped back up. Think of the battery as like a pump. It pumps it back uphill and it goes around again. And as it decreases, it gives up that energy. All right. Oh, I didn't do that one over there. Let's do it. Here's 2 ping pong balls. If I rub them so that the materials separate, they become charged, what do you expect to happen? Whoosh. They repel. That Coulomb force, there's a lot of charge now on each of these spheres. We'd say this one has Q and this one has Q. Put that into Coulomb's law, and the force the pushing them apart is overcoming their weight, trying to bring them back together. So you can, less long than this, again, because it'll bleed off, but let's see, we got 4 minutes. We'll watch. I think you'll see a little change within the 4 minutes, but probably not a huge amount. Now that we've done all this, let's go back to the charging by conduction and charging by induction that we did last time. It should make more sense, I hope. Again, if I make physical contact, oh, by the way, this is one of my favorite things. I do demonstrations for the whole department, each of their courses if they'd like it, and a lot of people ask for this same demonstration. But if they haven't done it much, well, let's just, basically they want to transfer charge to the electroscope so you can see it's charged. So they rub the rubber rod and then they do this. And then they think it didn't work. Then they come talk to me. I tell them what they did wrong and they do it next time. But I have to admit I laugh. So, but why? You should know why this doesn't work. You're on to, what'd you say? Yeah, is this a conductor or an insulator, do you think? Insulator. So can the charges move on it? No. So when I make physical contact, what charges are being transferred? Just the ones on the tip, not very many, so it's not enough. So some people get smarter and they go like this. Better, but still it was just those charges. You know, I like scraping it. Rotate it, try a different side. Anyway, that's how you need to transfer the charge. And it's the same charge. That's charging by conduction. That's now negative because this was negative. The induction was the more confusing one. Bring it near. What have we done to the charges in the electroscope? Polarized them. They now, think of this as the negative rod, and this is the electroscope needle. So if I bring the rod near, we're not physical contact here, and I'm going to take my finger and touch over here. What charges leave? The negatives. So then when I remove my finger, what charges are left? Net positive. So charge this back up, bring the negatives near, it pushes the negatives, they repel. I touch and give them a path. You can see the needle go down. I remove. Never touched it with this, but it's now charged. But opposite of what this was. That's charging by induction. Do you guys have any questions? Did pretty good, pretty good. I think that's a good stopping point. All right, you have a homework due this weekend for chapter 14, so don't forget that. Thanks, everybody.